All right, let's look at these. Number one. Acid-base reaction. We've got to find the most basic and the most acidic. Because the most basic atom will react with the most acidic H. Here's your bases over here. Everything's neutral, so you're looking for nitrogens because there's no anions. Which nitrogen's most basic, top or bottom? Bottom. Top lone pair is in a p orbital. Right? Lone pairs that are in p orbitals typically not basic. Bottom nitrogen most basic. Which H is most acidic? Alcohol or carboxylic acid? Carboxylic acid. So here's your mechanism. These electrons, they bond to H. The electrons in the bond there move on to oxygen. And that's what you get over there. You get that ion pair, which is called a salt.
Do we need to draw the resonance, if there is any?
No, did not ask for resonance, just showed complete Lewis structure. That's a fake structure there, okay? Questions about that one?
We can go ahead and draw all the electron lone pairs, if you want to draw all the lone pairs, or
You mean there were other lone pairs that are in the structures? Yeah. Yeah, for completeness, I should have showed lone pairs here and here. No questions on that one? I'm surprised there's no questions.
oh, do you want us to draw the arrows, what the arrows?
No, it did not ask for mechanism.
Okay.
It asked for Lewis structure of the products. But your mechanism is your apparently we want to focus in on something. Oh, did I hit Zoom? I'm not sure what I did. Zoom, auto. I don't know. Alrighty. Number two, show how the following compound will predominantly exist at pH of 8. Okay, you got an amine, it's a base, so the pKa refers to what? Conjugate acid. The pH is at 8, so are we on the high side or low side of 10? The low side, is that the acidic side or basic side? Is 8 on the autofocus off. I don't want focus. What do I want? Zoom. Zoom is digital zoom activated. How do you deactivate digital zoom? All right. Okay, 8 is on the acidic side of 10. Low side is acidic. 8 is on the acidic side of 10, so the proton is going to be on. When you put the proton on, it looks like this. Okay? 8 is on the high side of 7. The high side of 7 is the basic side. So the H is going to be off. And when the H is off, it looks like that. And that's how the molecule will exist. Questions?
So could you go over that one more time? Because I guess what I did, I picked the H to come off of the H2N and go over to the SH.
So you had this serve as an acid and that served as a base? Well, amines are not acids, they're typically bases. And that's not a base. What's a base? Anion or nitrogen, that's not a base. So why don't you have that act as a base and take a very unacidic H? pKa is here, this is a pH problem. pH is going to set your acid base, okay? To be a pH of 8, you got to have some hydroxide in there. Okay? 8 is on the low side of 10, proton is going to be on. Okay? H on. 8 is on the high side of 7, so we're going to have the basic species, that's H off. Has nothing to do with charge. When H is off, it happens to be a minus. When H is on, it happens to be a plus.
Do you want us to label the acid and base species?
No. As long as you show that, I think you should know what these are to get the question right. Okay, show the following the most stable Newman projection or confirmation. For us, the most stable is going to be the largest group's anti. Okay? Now there could be some argument here, and I noticed that on one. Okay, when I drew this guy, I looked through here, it says looking down to 1, 2, here's 1, 2, I gave you that. 1, 2, okay? I'm looking down that bond. On the front carbon, I see something going straight down toward my feet. What is it? Yeah, I see an F straight down, that's why I drew it straight down. I see a bromine, it's bold, so it's coming off the board towards you. If I'm looking here and I've got a bromine coming towards you, it's on my right. Okay? That's why I drew the bromine on the right. What's also on that carbon is an H going back, because this is tetrahedral, 2 in the plane, 1 forward, H back. If I'm looking here and there's an H going back, which means to the Hall, the H is on my what side? Left. So there's the front carbon. Now let's look back at carbon 2. There's something going straight up in the board. The isopropyl group. This ethyl group is going to the Hall. So as I'm looking down the bond, the Hall is to my left. So the ethyl is to the left. And then there's an H coming forward. So here's the original view. But you see, on the front carbon, the biggest is what? Bromine. On the back carbon, the biggest is what? H, ethyl, or isopropyl? Isopropyl. So I want to rotate the back, or you can rotate the front. Make the isopropyl anti to the bromine. And we get this here, bromine and isopropyl anti. And as you rotate the back, the isopropyl comes here, the ethyl comes here, and the H goes here, just like a wheel. How we do? Questions about this?
Wouldn't you also want the ethyl to be opposite of like the fluorine since it's bigger than a hydrogen? Or can you not do that?
The one argument you could say here is that you got a big group, a non-H between the two halogens. Okay? And you could make an argument. Where over here, in the original, between the two big halogens, there just sits a small H. Okay, that's what I said. There could be some argument. For us, the main thing we're going to look for is, and hopefully the answer would be more definitive here. Okay?
So would you have, if that was like on the test, would you have accepted either if we argued that having the H between the two halogens, would you accept that? Or?
It's a good argument. Hopefully if I give a question, it'll be more definitive. There is an argument here. Typically for us, we want what? Largest groups? Anti. Okay? You go with that, your answer would be, I put large groups anti. That's what you said. Right? Okay? We got lots of groups here. Main thing though is getting the original view right, because if you draw this with the ethyl here and the H here in the original view, well then that's wrong. Okay? Alright, one below we didn't quite get to. So I want to see how you can do here. Show trans, 1-T-butyl, 3-methyl cyclohexane in the lowest energy chair conformation. So, there's two ways to draw these guys. One is like this. This is sort of a perspective drawing, showing tetrahedral dashed in bold. Perspective. The other is in your actual chair conformation. Now this is trans. So the two groups are trans, okay? One's forward, one back. And we have nomenclature, 1, 3. So 1, 3. If I agree those are in a 1, 3 relationship, actually 1, 3, they're trans. T-butyl, that means tert-butyl. That's a tert-butyl group. 4 carbons. That's a common name. Methyl. Does everybody agree that this is trans, that compound? Okay, so that's nomenclature, understanding trans.
Is there another way you could have drawn it? Like if you started at the one position somewhere else, or do you have to start at the top?
No, you could have drawn it any way you wanted. You could put the
Yeah, that's
T-butyl
what I
here.
did.
But if you put the T-butyl here, then the 3 position is either there or there, and not there. So there's multiple ways to draw that compound. It's like there's multiple ways for me to show you my hand. Okay, thumb that way, thumb this way. It's all the same. Now this does have an enantiomer. That's just 2. We could have drawn that dashed in this bowl. That would have also been trans. That's beyond this question. That would have been right also here. Now, how do we draw that in the lowest energy chair conformation? First off, we've got to draw a chair. Now, I didn't tell you this last week, but whenever we do this, I don't expect you to draw in every single H all the time. What I do want you to draw in is the H that's on the carbon with the substituent. That way I can know that you know how to draw in all your bonds. And so these are up carbons, here, here, and here, and these are down carbons. This is an up carbon, so it gets an up bond and then an equatorial bond. Okay. Which group is bigger, T-butyl or methyl? T-butyl. So you want that group equatorial or axial? Yes, T-butyl equatorial. So what I did is I put the T-butyl equatorial. That's where it wants to be. Then from there, you say, okay, now where am I going to put the methyl? First off, the methyl is the 3rd carbon away. That's 1, that's 2, here's 3. If you put the methyl there, that's wrong, becomes 1, 2. Unfortunately, I see lots of answers where the methyl's not even in the right place in such a question. Okay? We're drawing 1 T-butyl, 3 methyl. Now the 3 is either here or here, either way you go, and again, that can be an enantiomers, it works here. Is the methyl going to be axial or equatorial?
Axial.
For my answer, it's axial. Why is it axial? Okay, what if it was on the 2 position? Would it be axial or equatorial? So, how do you do this? Okay, how do we do this? And we didn't get to this point on last Friday. We were rushing at the end a little bit. Let me draw in the H's here. Okay? There's an H, that's a down carbon straight down, and then the equatorial would be parallel, not to this, but this. And let me label those A and B. I'll label that one up there C. Which one is trans to C? A or B?
B.
Which one is trans? Which one is trans to this?
B.
B.
B. B is trans. How are we deciding that's trans?
Because they're going up.
Because up versus down. Okay? This C, is that going up or down? Up. Is that going up or down? What you're doing is you're comparing it to the other thing there. Is A up or down compared to the other one? It's up. Is that up or down compared to the other one? What's the other one do I mean? The other one means the other thing on that carbon. It's the T-butyl. Okay, is the H going up or down compared to the other thing? Is that one going up or down compared to the other thing? Up. Both of these are up. These are cis. And that one and this one are trans. Because if I hold a ring and I make that ring flat, although it's not really flat, and I have one going up and one going down, are they cis or trans about the plane? Trans, okay? It's up and down here. Okay, that's how you get it. So, my methyl, is it going up or down compared to the other thing? Up. Is the T-butyl going up or down compared to the other thing? Methyl's up, T-butyl's down, so they are trans, okay? I drew them trans. That's how you do these. Please don't fall into the trap, well, this is axial, that's axial, so they're cis. No. Two things that are axial can be cis if they're in one, if they're maybe 1,2 or 1,3. But two things that are axial can be trans if they're 1,3 or 1,4. It has nothing to do with if they're both axial or both trans. It has to do with up or down compared to the other thing. Question, Sarah.
When we're doing the chair confirmation, do we have to draw like the dashed and the bold lines or the fact?
No, you do not. You do not draw dashed and bold in chair
Okay,
confirmation
so the
or
fact that up
Newmans.
and down.
Newmans or chairs do not get dashed or bold because things are straight up, straight down. That's all in plane. This is actually a little bit forward, but you don't do it in chair. You do not do dashed or bold in chair or Newmans. It's more implied. You also don't do it when we do Fisher projections in during test 2s. Whenever you do special projections, you don't do dashed or bold. Okay. Now you could put the methyl here. Why did I put the T-butyl on that carbon right there? Why did I put it here? For this. It's the same thing here. If you're going to draw that compound from that name, why not put a T-butyl here and then a methyl? Once you put that, then you got to put the methyl 3. Put the methyl there. Or why not do it like this? Why not put the T-butyl here and put the methyl here? Those are all that compound. So why did I put the T-butyl here? Because this is how I did it. I draw my chair and then I say, I got to put a T-butyl and a methyl. I just like to start right here. Maybe you like to start there. And I want my T-butyl how? So I drew it equatorial. From there, well, the directions usually are going to say drawing the H's with substituents. It didn't say that here. But if you're drawing the H where there's substituents there. Now that I got that there, I got to say, now I have to put the methyl in a certain position. Because I can't put it there because that would be 1,4. The methyl's either got to go here or here. I chose here. Since this is down compared to the H, and I want the methyl trans, I put the methyl up compared to the H. And up is straight up. And that's why that ended up like that. Just like that. Okay? One at the bottom. Which is least lipophilic? I don't think we've said lipophilic. What does lipophilic mean? It likes lipids. Lipid is a term meaning fat. What does fat mean in organic chemistry? Fat means lots of hydrocarbon. Okay? Plain, boring hydrocarbon is called kind of fatty or lipophilic. Okay? Which one is least fat-loving? You hear lipophilic in biochemistry or cellular biology, we talk about lipophilic membranes. Okay? This is membranes that are composed of sort of fatty chains that come from certain molecules. Or your fats. Okay? Least lipophilic is going to be least fat-like or least hydrocarbon-like. Which one is it? It's the one here. Most polar bonds, it's also got an ionic charge. Okay? The opposite of lipophilic would be like hydrophilic. Hydrophilic means it likes water. It's going to be polar. Then you have phobic terms like hydrophobic. Hydrophobic and lipophilic is the same thing. Okay? So those are some generic terms you just need to know. Alright? Everybody get that one?
hold on, you wrote, okay, now I'm confused. Because at the bottom, it says also most polar and hydrophilic.
That's what I just said. The opposite of lipophilic is hydrophilic.
Yeah, so if it's lipophilic, then shouldn't it be?
No, it's least lipophilic,
Oh, okay.
most hydrophilic.
Okay.
It's the least fat loving, it's the most water loving.
Is vitamin A the most lipophilic?
A and E are kind of similar. They both have lots of hydrocarbons and they all, well, that one does have 2 hydrogen bond acceptors. So maybe you can make that argument. They're both pretty similar. I think A and E are both considered fat-soluble vitamins, where this one is not considered a fat-soluble vitamin. Why is that important? Because then the vitamins go in certain places. Okay, vitamin E has activity in fatty tissue. That's it. Okay? Right.
I have a question on the first one again, for the N, the bottom N. Why is that the most basic? Because I know,
Okay, what type of orbital is this lone pair in?
because I thought that was in a P orbital.
That there? No. Everybody graph that nitrogen, everybody. Hybridization, very simple. Just show the hybrid orbitals, fill in your electrons. Okay, what's the hybridization? sp2. That means how many hybrids? 3. What's left over? P orbital. Okay, what type of bonds do you see this nitrogen making? I see sigma to carbon and sigma to carbon. Because that over there is a sigma and a pi. So I said double. It's a sigma and a pi. Okay, let's make a sigma and a pi. Sigma to carbon, pi to carbon. There's your double bond. What else do we see? Another sigma to carbon. See 2 sigma to carbon. One here, one there. What else do you see? Lone pair. It has to go there. What type of orbital is a lone pair in? sp2.
And the other one is the P orbital.
The other one's in the P orbital. What's the hybridization of this nitrogen? It's sp2. That's that exception thing, right? Because anytime a lone pair is next, there's a P orbital here. Okay? It's P orbital there, it's all the way around. That's how you make that pi bond. That's going to want to play with the P orbitals. That's sp2. What type of bonds do you see it making? I see sigma bond to H, sigma bond to H, and what else? Sigma bond to carbon. Where's the lone pair? Right there. Okay? This is why I suggest graphing it. I don't see any books do this really beyond carbon. I suggest graphing it. Now you know where the lone pairs are. What do we say about a lone pair in a P orbital? Not basic. Not very basic. Okay? This is your basic lone pair.
So would the only degenerate orbital for nitrogen be 1s here?
Come again?
Would the only degenerate orbital be 1s?
Well, these three are degenerate.
Oh, okay, so they're the same.
It just means they have the same energy. Okay, test tomorrow. Any questions about it? Format. We have some nomenclature. Okay. Usually I have some multiple choice questions near the beginning. You have plenty of multiple choice in the workbook. Then we'll move on to short answer like the quiz here. And then there will be a page of IRs, just like in the workbook, where there's compounds at the top, you assign a compound to an IR. In terms of topics, well, everything we've covered, what have we covered? We covered structure, hybridization, everything associated with that, bond lengths, bond strengths, bond angles, Then we have physical properties, IMFs, including hydrogen bonding, solubility, melting point, boiling point. Then we have acid-base chemistry. Then we have miscellaneous things with structures, nomenclatures, trans, constitutional isomers. Anything else? What else have we covered?
The chair.
Then we moved into the chair and the Newman confirmations. Let's look back at that handout and let's do some examples there, finish up that. Energy levels, this will be on the blue handout. I think we did the first one here, but we didn't do the other two. Looking down the 2,3 bond showed the lowest energy conformation, okay? With acyclic alkanes, what does acyclic mean? Non-cyclic, okay? We're looking to do Newman, circle, circle, dot, dot. 2,3 bond, that would be 2,3. Looking down that, so we're here. Down there. Okay? 2,3. 2 carbons in the front. What's on the front carbon coming straight down towards my feet? I'm looking right down the board. What's coming straight down the board? Nothing. What's on the 2 carbon going sort of up and towards you? Bromine, see how it's coming towards you, it's bold. Okay? So if I'm looking at it, and it's coming towards you, like that, well, that's on my right. So I'm drawing what I'm seeing. I'm just drawing it. I see a bromine going to the right. What's on carbon 2 going back toward the hull? So if I'm looking through here, and it's going to the hull, that's on my left. I see an H on the left, so as I draw, I'm drawing what I see. I'm drawing, this is what I see. Okay, on the back carbon, there's something going straight down. What is that? Ethyl. So it's like it's eclipsed with the methyl. I'm just going to draw it a little bit to the side there. There's a methyl here going back. So if it's going back, it's to the left. So it's eclipsed actually with the H. And then there's an H coming forward. And it's eclipsed with the Br. So as drawn, that molecule is in a eclipsed conformation. Really. If we can take it off the board and sort of look at it, you'll see. Well, is that the lowest energy conformation? No, we want staggered. Not only do we want staggered, we want what? Oh, largest group's anti. What's the largest group on the front carbon? Bromine. What's the largest group on the back carbon? So bromine and ethyl. So I'm going to rotate that back carbon. Really, I want the ethyl here, just a little bit. And so the front carbon, I'm going to leave the same. We've got H, Br, methyl, CH3. Now the ethyl's going to be here. And when the ethyl comes here, what's on the back carbon? Methyl? Where does it go? It's going to go here. And then the back H is going to go here. And so we have two groups anti. I'm not going to make them all. Does everybody see what we're doing here? I got a certain conformation here. Do I need to make a model?
I
Question?
have a question. Could you do the bromine and the ethyl on the top and bottom, or is the reason you did that way is because it's the least amount of rotations to make it empty?
What do you mean top and bottom?
Like the very, like going straight up and straight down instead of on the sides?
Well, how did you draw it originally?
I drew it like that, but I guess, but then with our.
Oh, from here you can just rotate the front carbon if you want.
Okay,
And put the bromine here.
yeah, that's.
Yeah, it did the same thing. It's as if we just turned the board and did it like that.
Okay, so it doesn't matter which way.
As long as it's the same compound. As long as it's that compound and with the bromine and ethyl anti, then you're good.
Professor, what's the difference between eclipse and sin?
Syn is where both the biggest groups are both on the same side, and they're eclipsed. Syn is a type of eclipse. Where anti is actually a type of staggered. There was another question over here. The one on the end there, looking down to 4-3. Let's see. What's the name of this compound?
Three methyl 4,4. 3,4,4. Is that what you do? Try that.
I think the name of this compound is 2,2,3 trimethyl. Iodo comes first. Does that look right? 4-iodo, 2,2,3 trimethylpentane. I got 1, 2, 3, 4, 5. There's no other way to get 5, is there? What's on that? I got methyl, 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 iodo. 2, 2, 3, trimethyl. But the iodo is going to be listed first. It's at the 4. How's that name look?
Could you switch the numbering of the carbons so that one's on this side?
Well, if the 1 was here, that would be what? 2, 3. It'd be a 3, 4, 4 trimethyl. And iodo would be at 2. Which is better, 2, 3, 4, 4 or 2, 2, 3, 4? That's better numbering. Okay, so we're looking down the 4-3 bond. That's the 4-3 there, right? 4-3. That means the 4 is in the front. So we're looking down this bond right here. Okay? Now the front carbon. Okay, here I am. Pretend this molecule's out here. Looking at what's going straight up. Methyl. What's on the front carbon coming towards you guys? It's actually coming down towards you guys. Iodine. And what's on the front carbon going to the hull? Yeah, it's also a little bit going down. The iodine's coming this way, the H is going this way. Now let's look to the second carbon back there. There's something going straight down. That's a T-butyl group. There's something on that second carbon there coming towards you guys, and up a little bit up and towards you guys. Up and towards you guys. If it's coming towards you guys, that's my left. I'm seeing it coming to my left. And what's on that other carbon? See, there's an H going up into the hull. To the hull to my right. I see an H to the right. Okay? I see an H to the right.
Should be good.
So that's how it's drawn on the board.
Then you need to rotate
Looks good to me.
the largest group.
Can iodine be bigger than that? Looks good.
Yeah. Now there's tables that you can look up. You don't have to memorize these. Iodine is going to be bigger than the methyl. Iodine is way down the periodic table. Even though it's got H's, that iodine is huge. Iodine and T-butyl. So let's rotate the front carbon and let's move this iodine up here. We're going to move the iodine up. That's going to make the methyl come over here. And it's going to make the H come over here. That's the front carbon. We just turned it. Or how many degrees did we turn the front carbon?
Or whatever,
120 degrees. Back carbon we're not going to change. The T-butyl is going to stay there. Methyl, H. And now we have our big groups, anti. And so pretend this is the molecule, okay, I'm not going to take time to do it. It's walking down the street. Originally, the T-butyl and the iodine were, what's the relationship here, T-butyl and iodine? What do you want to, they're not sin. Sin is where they're eclipsed. Sin is where the iodine is straight down on top of that. Yeah, here they're gouge, okay? Is that how it's going to predominantly exist? Or is that iodine going to want to move away from there because of electron repulsion? That front carbon, okay, pretend this is it. That iodine is going to want to move away from there and it's going to rotate more up, be away from that back group. When it rotates up, now we call that anti, and that's how it's going to exist. Question?
I know you said that you would expect to know the size, but what would you say as far as like a ethyl group once it starts being that versus the halide? So we just assume that the two carbon groups?
Yeah, I have to be careful and give you something that's going to be very clear. Okay. Otherwise, you've got to kind of look up tables. And sometimes, you know, actually a chlorine is, okay, plug your ears. Chlorine is actually, I think, a larger steric value than a bromine, even though it's smaller. And so if you look in tables, you will sometimes see some oddities. For us, as the halide gets larger, it's larger. As the alkyl group gets larger, it's larger. Okay? And I'll try to give you questions that are very clear. Sometimes I don't anticipate it, or really I need to do it ahead of time.
Professor, in this case, could we have rotated the back carbon?
You can rotate either carbon you want. As long as in the end you got the largest group's anti and it's the right compound. Now I did ask you to look down the 4-3 bond. If you do it as if you're looking down the 3-4 bond, it's not going to be right. So I wanted it as if you were looking down the 4-3. Meaning the 4 carbon in the front. Okay, did we do these on the back? I don't think we did. Okay, up here. Now we can answer these. I told you how to do these at the very beginning. Are these two halogen cis or trans? Well, if we draw the H here, it's like that, and that one's like that. Everybody agree? Well, those are up carbon, that's an up carbon, that's a down carbon. Okay? Are these cis or trans? Trans. Everybody clear on that Y? That's down compared to the H, that's up compared to the H. One's down, one's up, trans. Now, if we were to draw that in perspective drawing, it would be trans, and it would look like, well, first off, the halides are in what relative positions? 1 what? 1, 4. Okay? So if I put the chlorine there, see here we need to show dashed and bold. Where am I going to put the bromine? Here, right? It's going to be dashed or bold. Bold, because it's trans. Okay? That would be in a perspective drawing.
How do you know which one to make dash and which one to make bold?
You're right. Here it doesn't matter
Okay.
because of a quirk, and this is not really a quirk. Sometimes it would. If it did matter, that's where I said it's beyond this, that's test 2. Now, of course, if they're both bold, then it's not a question. Okay, so what was the first one? Trans? How about this one? Cis or trans? Let's see, that's a down carbon. That's a down carbon, right? So what is this? I'm a cis. Okay. How about this one over here? Trans. Okay? It has nothing to do with both. What was this one over here? Trans. Well, over here they're both equatorial. Over here, one's cis and one's axial, one's equatorial. So if you follow the trap of saying, well, that's axial and equatorial, they're opposite trans, then you see over here they're both equatorial. So is that cis? No, it has nothing to do with that. It has to do with whether up or down. Showing a perspective drawing, while I did the first one in the perspective. Can you show that one over there in a perspective drawing?
So for that one, would it matter which one's bold, which one's dash?
It actually does, but we're
Okay,
not able to address that right now.
okay, so right now, it doesn't matter which one, but what direction we're in.
Which UD ones is the,
Let's do it and then let's see if we got it right.
Okay.
Now a bromine, a fluorine, and a, what's the other group? Common name of the other group? Isopropyl. Now I'm just going to do it how I would do it, okay? Now I'm going to kind of get it right with that other thing that we don't know yet. Let's say the isopropyl is here and it's going like that. That sets the stage. Now we have to do everything else relative to that. Now where do you want to put the fluorine? Here? It's next door. Okay? Now I'm actually going to put it on this side. Do I want to put it dashed or bold?
Dash.
Why dash? Because they're cis. Everybody understand why they're cis? See how they're both down compared to the H's? If we drew the H's there, there's one like that. This H is like that. So I drew them cis, meaning both dash in the perspective. See, they're both down, Here, they're both back. But if I turn the board like this, then they're both down. Okay, now where you want to put the bromine? Here? No, we skip, the bromine's here. Is it dashed or bold?
One more, you went too far.
Those are the bottom. It's directly down.
Not the next chart, but the next one. That's good. Not that one, but that one. Yes. Good. Here is bold. Because the F and the BR are what? Trans. There you go. There it is in perspective.
It doesn't matter where you start.
Doesn't matter where you start, as long as you, are they the same compound? If you name them, they should have the same exact name. Same connectivity. The dashed and bold would come in a descriptor in front of that name. Zach?
Okay, I was gonna ask, if we were to draw the perspective drawing, would it matter if we did the fluorine and isopropyl as bolded and the bromine as dashed?
For us here on test one, it would not matter. In real life, in actuality, it would, but we're not able to address that. That is a stereochemical, stereoisomer thing, and we're not covering stereoisomers right now. The only thing we cover with stereoisomers is that we know what a stereoisomer is compared to a constitutional isomer. Okay? And if you just change dashed and bold, you're not changing connectivity. You may think you are, but just like this. If I change my arm from here to here, I'm not disconnecting it from my shoulder. It's still connected at the same place. Same connectivity, just different orientation. Did we cover everything here? I noticed that I didn't include this handout here. It's actually a sort of a wild example of a paper where they did some computational work, and the 6 isopropyls it's actually, well, it's all trans, but they're actually all axial. Plug your ears. All right? Always exceptions to chemistry. It's a wild and crazy science, right?
For that one to the right, is that one that you would not put on the test then? Because it's got that isopropyl group in it versus chlorine? And we can't tell which ones there are. Which one would,
Now, we're not doing rotation here.
well, we want to know which one's equatorial, the strongest one would be equatorial, right?
Oh, you did a ring flip?
Or that one that's showing right there.
Which one?
The one right
Here?
No, no. Part E.
Here? Didn't we do that one already?
No, these are,
Did we do these two?
no.
Oh, we didn't do these two. Okay, let's do these. Lowest confirmation. Let's do these quickly. Okay. Okay, which is bigger, F or BR? BR. Okay. Now, question here. Can I make both BRs equatorial? If you don't know that yet, let's try and see. I'm going to make one equatorial because one wants to be. Can I get the other one? If that one is equatorial, there's an H there. Where's the next BR? It's on the next carbon. Is that one going to be equatorial or axial, the BR? Well, there's cis, so that means it's got to be down compared to the H. Down compared to the H is what? Yeah. See, these are cis. Now the fluorine is going to go where? Either here or here. Let's put it here. If we put it here, that means this is 1, 2, it's 1, 2, and then we get to the fluorine. And let's not worry about the stereochemical thing. Now this fluorine, is it let's say up or down. Is it up or down? opposite that bromine, so it's up. Up here is axial-equatorial. Yes, up here is axial. And so these are trans. All right. Is that the best conformation? What do we have here? We have one equatorial and two axial. Is that best, or should we do a ring flip? If we do a ring flip, what's it going to look like? Now, here we go. If I do a ring flip, I can pull this down and put that up and do an actual ring flip. But I don't actually have to draw it like that. I can still draw it like this. But when we do a ring flip, what do we know? What happens to all axials? They go equatorial, and all equatorials go axial. So now, when I do a ring flip, I'm going to do it this way. I'm going to now put one BR, I'm going to put this BR axial. I'm just going to do it like that. So if that's axial, how is this one going to be? Well, there's cis, and cis here is going to be do I agree that those are cis? See, there's cis here. Okay? Now, if this BR is up compared to the H, how's the fluorine going to be? It's going to be, they're trans, so it's going to be down. And so that's actually the ring flip. Now again, it's not where I pull this down and push this up. That's it. It just may be grown a little bit. All right. Maybe do a ring flip, all axials, okay? So which is better? In both, we have a bromine equatorial. In both, we have one bromine equatorial, one bromine axial. So it's kind of a wash. So then you say, well, would you rather have this be equatorial axial and a fluorine equatorial, or this being equatorial axial and a bromine being and a fluorine being axial? This is better. So there's your lowest energy conformation for that compound.
Future reference, we'll do a ring flip that way, mess up the stereo chemistry by not actually flipping the combination of the GLC link. Like those are stereo isochemistry, as opposed to just doing a ring flip.
You're very right. Yeah, good. You're right. Yeah. I would talk more about it. We need to move on. We need to start new material today.
So for testing purposes, that would be okay?
Yeah.
For this test?
Yeah. I say yeah because you'll probably see in the answer key ones that are done like that. And I'm not considering stereoisomers. Because if I did consider stereoisomers, we would have to talk about that probably 15 more minutes. Just to explain. And so it's a little bit beyond this right now. Okay, let's take a 3-minute break and then we'll start new material. There's going to be 2 handouts. We'll pass them around here. One yellow, one white.
Could you say again why that one's
Oh, this is new material. It's more than just that. In this one, in both, the largest groups are equatorial. Bromine is a larger group, it's equatorial, you got an equatorial. You can't have both equatorial. So that becomes a wash. It's the same, it's essentially the same in both. So you let the fluorine decide. You'd rather have it equatorial.
Drew, would that be correct for that?
Going to cis. Nothing is cis, going to full.
But you would want to eliminate the two at the two. And so for purposes of this test, we'll do it instead of actually doing the
See here you. Either way you go, the ring clip is also going to have some chlorine in the so the chlorine will like a what? Let that decide.
And so this, in this case, it would be better to do wrinkle. Trans, you could have them both active. Cis, they're never going to be like that. Cis, they're always going to be guided for well, just direction. Opposite's going to be more chemical. Whatever, we're done with Where at? That's some
You just want to see me bend over?
This answer kit we posted in Science Hall, 3rd floor. Let's look at Intro to Alkenes. We're starting new material. This is test 2 material. Alkenes. Compounds with the carbon-carbon double bond. Got to have at least 2 carbons. Simplest alkene would be ethene, also known as ethylene. You can polymerize it and make polyethylene. C2H4 formula, of course, 1 degree of unsaturation. We see the pi bond, that's a degree of unsaturation. Ethylene's a gas. It is used for ripening of fruit. If you expose a fruit to ethylene, it will ripen faster, like banana. Why? No, that's a good question. Used to be used as an anesthetic, knock people out, not much anymore. In terms of more complex alkene, here's one here. You got the carbon-carbon double bond. You got other things on there. You got this ether with a distal tertiary mean, 2 benzene rings, ethyl group here. Put these together, you get tamoxifen, it's a breast cancer drug. One thing, the carbon-carbon double bonds in a benzene ring are not really considered alkenes. Okay, that's considered aromatic. Your alkene is here, not in the benzene ring. Benzene ring double bonds have different chemistry. Okay. Nomenclature. Just like with alkanes, we find the longest continuous chain. But the carbon-carbon double bond has to be in that longest continuous chain. So, 1, 2, 3, don't even count that because the double bond's not in there. Might as well start on the end of the double bond. 1, 2, 3, 4, 5. Either way you go, you got 5. And so the longest continuous chain gives us pentane. But since it contains an alkene, it's named as an alkene, and the ending becomes -ene. And so we get pentene. That means it's a 5-carbon with a double bond in it. But where is the double bond? Because the double bond could be here, here, and here. So you have to denote where the double bond is. You do that by denoting which carbon of the chain does the double bond start. Your double bond is basically almost treated like a substituent. And the double bond is at the 1,2 position. And you say that this is a 1-pentene because the double bond starts at the 1. You don't have to say 1,2. It's a 1-pentene. I circled a 1-pentene. Now what is on the 1-pentene? There's a methyl at the 4. So we have 4-methyl. That is a dash there between methyl and 1. 4-methyl 1-pentene is the compound there. Aaron?
So you gave the double bond the 1 because of alphabetical order, is that,
No.
because of where it is? Or?
Carbons of double bond gets lowest numbers.
Okay.
Double bond is a priority. Double bond takes priority in your numbering. Name the one on the right. Longest continuous chain. 1, 2, 3, 4, 5, 6, 7, 8.
No,
The double bond has to be in
But the double bond has to be in it. Might as well start right here. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. I see a 7 right there. So it's not heptane, but what? I circled heptene. But where's the double bond at? Is it between the 1 and 2, or the 2 and 3, or 3 and 4? We also have a 1 at the 1 position. 1-heptene. 1-heptene is circled. What's on the 1-heptene? Three what? 3 propyl 1-heptene. Name the one with the chlorine. Oh, we did this. You guys on my left, the chlorine compound. You guys on my right, do the one with the bromine. Longest continuous chain? Taylor?
I got 6.
1, 2, 3, 4, 5, either way you go 6. Okay, so that means it's a hexene. Where's the double bond at? 1, 2, 3, 4, or 1, 2, 3, 4?
Starting from
You got 3, 4 either way. So what's it going to be?
the lowest number of constituents.
It's going to be 3, 4. But for which end? How are we going to decide beyond which end? Have the remainder of the substituents be lowest numbers. If this is the one end, double bond's 3, 4 given, but then the first substituent is not until 3. But if this is the one end, double bond is also 3, 4. So either way you go, it's a 3 hexene. But we want this to be the one end. Why? So we can have a substituent at the 2 and 4. So what is at the 2 and 4? 4-chloro, 2-methyl, 3-hexene. If I'd come the other way, it would have been a 3-5. Instead of a 2-4. Double bond gets priority, double bond gets lowest number. If you got a tie, then you give everything else lower numbers.
For alkenes, are we only talking that there's only going to be one double bond then for alkenes and something else?
For now, during test 3, we will cover dienes and trienes. That's where you would just give multiple numbers for your double bonds. These compounds here do require stereochemical descriptors. Okay? The 2 up above did not. We'll have to come back to these 2 after we define what this means. Okay, one the bottom. Somebody got a name?
6, 1, 2 hexene.
1, 2, 3, 4, 5. Longest continuous chain, pentene. Is that right? Where's the double bond? 2. That means this is the 1 position. And the bromine's where? But if this had been 1 here, we could have got a 1, 2, 3. We could have got a 1, 3. But double bond gets priority for that number, right? Okay. 5-bromo 2-pentene. We can also have cycloalkenes. The double bond is always at the 1 position. Because in the ring, the 1 position can be anywhere, but since we give double bonds priority, it's at the 1. And 1, 2. Because after the first carbon of the alkene, you then number the second one. You include it in the 1, 2. So this is a what size ring? It's a cyclo... Just if the double bond wasn't there, what would it be? Be cyclohexane, but we have a double bond, so the cyclohexene, where's the double bond? 1 position. We don't have to write the 1, okay? But we act as if it's there. What's on there? What are the numbers for the bromine and the propyl?
3, 4, 5. I guess you could go.
Bromine at the 2.
What's the position of the bromine?
3.
1, 2, 3, 4, 5. 3 bromo, 5 propyl. That's all one word. Cyclohexane. We could have called that 1, 2 that way, but then it would have been 4, 6. 3, 5 is better than 4, 6. Name the guy on the right with the chlorine.
Two chloro, 4 ethyl, cycle.
Brenna, you get some curls? Somebody got it? Adrian? Not Adrian. What's your name? Elena.
The 2-chloro-4-ethyl
2-chloro-4-ethyl cyclopentene.
cyclopentene.
Does anybody have a different name? You don't?
1-chloro-4.
Yes. 1-chloro-4-ethyl cyclopentene. Yes. There's a double bond. Which carbon and double bond you want to be 1? Top or bottom? Bottom. Why do you want that one to be 1? So the chlorine can be 1 also. 1, 2, 3, 4. Which is better, Elena? A 1-4 or a 2-4?
1-4.
Don't worry. Usually nobody gets that right. Usually everybody always says 2 chloro. Everybody see that one? 1 chloro? If the double bond start, if the one position can be either place, you would rather have it where a substituent is. Okay? There are some common names that include alkenes. If you have just a plain alkene, there's 2 H's and 1 H, and then something that's called a vinyl group. Okay? And this is called vinyl chloride as a slang name. Okay? And if you polymerize it, what do you get? Polyvinyl chloride. PVC? Okay? You're like your sprinkler pipes. Okay? Allyl group is where you have a plain alkene, a CH2, and then something. Like allyl alcohol. Okay? It's an allyl group. And at one point we'll do chemistry next door to an alkene, and we'll call that the allylic position. The allylic position. And when we do that, I'll say, remember when we talked about the allylic position, and you'll go no. So then I'll refer you to this moment right here in time, and I'll say, okay, that's the allylic position. So that's it. Okay. You remember this thing about alkenes, they can't rotate of the pi bond? Because they can't rotate, we have isomers, potential for isomers. By the way, anybody interested in a scholarship for $16,000 to $17,000 a year? We have a scholarship program for science majors who are interested in going to teaching, called the Prestige Program. Here are the current scholars. Biology, chemistry, physics, math, any such STEM majors interested in going to high school teaching, you can get both the BS and MAT degree in 5 years. Starting junior year, you get scholarship for like $16,000, $17,000. Want to pick up a handout if you're interested? Teaching would be a very good career. We have one scholarship remaining, and we're actively looking to give it away. And we need an applicant. Okay. This is a National Science Foundation funded program. We have one scholarship remaining. Pick one up if you want to talk about it. Okay, alkenes. Both of these are 2-butene. Everybody agree they're both 2-butene? 1, 2, 3, 4, double bonded to 2. They're both 2-butene. But they're different compounds. Because one, see what ends up being the methyls coming off of the alkene. One of them, they're trans, they're opposite. The other, they're cis. Okay? Now, if this was an alkane, and that's butane right there. Well, is this 2 different compounds? No. With butane, that's 2 different conformations. That's just like if I hold my hands up, am I a different person? No. Okay? This can rotate. Conformations versus different compounds. See, these cannot rotate. The methyls are stuck there. I mean, if you had a person come in and their arms were stuck like this, and then you have one come in and stuck like that, can you say that they're just 2 different people? That's the way they're stuck. They can't interconvert between the two by rotating or moving. 2 different compounds, 2 different sets of physical properties. Okay? Those are the same. That's just the same compound, different conformation. So what do we have in front of the name? A stereochemical descriptor. Cis versus trans. Otherwise, same name. These are stereoisomers. Stereoisomers have the same name, because they have the same connectivity. Different stereochemical descriptor. Now, then we can ask a question down here. Is this cis or trans? Is this a cis or trans compound? Is this a cis or trans compound? I don't know. Cis and trans is most convenient and really only applicable if you have 2 groups. Okay? If you know what you're talking about. If you don't know what you're talking about, it's ambiguous. What we can say here is that the methyls are cis, and this methyl and this chlorine are trans. That is irrelevant. They're on the same carbon. I mean, okay? So as a whole, it's neither. Whenever you have more than 2 substituents, to name it to put the stereochemical descriptor, we use what's called EZ nomenclature. And it takes it a step further. To do this, we have to, E and Z is based on priorities. On this end, you have 2 different carbons. What's on this carbon? What atom is that carbon bonded to? Carbon. And what else is it bonded to? H. You look at what it's bonded to and which one is high priority. Priority is based on atomic number. Higher atomic number, higher priority. Which is high priority? Carbon. Which is higher priority? Carbon or chlorine? Chlorine. Chlorine. Your high priority groups are trans. And when your high priority groups are trans, it is E. It gets designated as E. Alright? That's how you do this. And that's what's shown below. So we know this is E. We just did it. What's the name of this compound? If we name this longest continuous chain, everybody agree that's 2-butene? What's on the 2-butene?
2-chloro. Okay? Are these the same compound or different? These are different. Here, the two methyls are cis, and here they're what? They're the trans. Can they rotate? Can this rotate and become cis? And like, no. They're two different compounds. They're stuck that way. They're both 2-chloro-2-butene. I mean, isn't this 2-chloro-2-butene? 2-chloro-2-butene? But this one is what? E. Put an E in the front, sometimes it's in parentheses. So that's E. E is what? And the high priority groups are trans. Here's how I remember E. E is a vowel, and it's where the high priority groups, they're trans, but also known as opposite. And opposite starts with a vowel. So E is a vowel, opposite starts with a vowel. Okay? Now, what's high priority groups here? On this carbon. And the carbon or H? Carbon. How about over here? Chlorine or carbon? Okay? They're on the same side. What do you call that? That gets a Z. Same exact name. E and Z. Stereoisomers. They just have different stereochemical descriptors. How do you remember Z? Well, the high priority groups are on the same side. Okay? So when you have more than two groups, you use E and Z nomenclature.
What is the Z, does it stand for anything else? or-
It's probably German for something. Okay? In the end, it's pretty easy. Okay. All right. I'll be here all week. So that's what we just did, okay? So assign these as E or Z. What we got here? F for carbon. F. Bromine or chlorine? Bromine. What we got? Z. Before we move on, let's go back to the front page where I said that these two here required stereochemical descriptors. I'm sorry. Let's go back. E or Z? High priority group on this end. F for carbon. Okay. It doesn't matter what's attached there. It's one atom at a time. One atom at a time. You don't add it up and okay, big old thing. It's F for carbon. That's what's bonded here. Over here, H or H?
Doesn't matter.
So is this E or Z? Cannot be determined. Why can it cannot be determined? Because it does not have E or Z stereoisomers. Okay? See, this guy can be drawn like this. What was that? What is this? That's E. This has a stereoisomer. An alkene stereoisomer. It's like cis and trans, okay? Z and E.
we put the ethyl group up, or the propyl, and put the fluorine down? Are these different?
Same carbon.
This is the same compound. This is just a compound flipped over. See, if I flip this over, if I just flip it over, I mean, I could draw it like that. If I flipped it over, it would be if I just took this and did it like this, it'd be that. I mean, these are the same, but neither one is this. And both of these, the bromine and methyl are trans. The bromine and methyl are trans. Ah, but now the bromine methyl cis. Okay? Here, this doesn't have a stereoisomer. And we're looking at the alkene. No alkene stereoisomer. Not every alkene has a cis-trans, you know, like a left and a right hand. That one doesn't. How about this one? E or Z? Or is it chlorine or carbon? Carbon or carbon?
Same.
Same. When it's the same, you keep going. All H's are all H's. It's the same. Huh, is it E or Z? Whenever you run into this thing, what does that mean? No stereoisomer. That's what it means. Because what if we draw this with the propyl up here and the chlorine down? It's the same compound. Okay?
So that one top, so you put the bromine for the right side, the right.
On this carbon, bromine's high priority. On this carbon, fluorine's high priority. So they're on the same side.
Oh, so fluorine beats the methyl.
F beats carbon. Atomic number. One is the
Oh,
higher.
we're not looking at the stuff attached to it.
No. Let's look down. Okay, let's look at the next page real quick. Tamoxifen, breast cancer drug. Is it E or Z? High priority group, oxygen or carbon? Oxygen. Carbon or carbon? Does this have a stereoisomer? If I drew the phenyl group down and the ethyl up, switched them, would it be a different compound? Yes, because see here the phenyls are trans. I could also show it with the phenyl cis. Okay, so it does have E and Z. Question is, how do you deal with it when it's carbon and carbon? If the first atoms are the same, you look at what's bonded to carbons. Not everything, but just what's directly bonded. And you list these in priority themselves. What's bonded to the first carbon? What's bonded to this carbon? A CHH. So we list those. CHH. What is this carbon bonded to? Well, that's a double bond to C and a single bond. Double bond to C is like it's bonded to two C's. So it's like CC and C. C, C, and C. Then you look at these. Which is better, C or C? Well, that's a wash. Which is better, C or H? So that becomes the high priority group. We'll do more examples. So this is the high priority group that. So it's the same side. Tamoxifen is Z. If you put the phenyl over here and make it E, it's not a breast cancer drug. It's not active against cancer. Back to this alkene. Does this have a stereoisomer? You need to be able to answer yes or no, and then if it is, show it. Okay? Well, the one thing is, do E or Z. Can you do E or Z here? What's our priority group on this carbon? Carbon or H?
Carbon or chlorine? Chlorine. So what is this? Z. So whatever the name was, we put a Z in front of it. And if you can do E and Z and get an answer, that means you could also have the other one. You can also have E. How would you get E? Well, just switch one in. The isopropyl and chlorine are cis here. In the E compound, they would be trans. Down below, E or Z? Well, actually, this doesn't need to be E or Z. When you only have two groups, you can just use what? You can just call that trans, okay? Because there's no ambiguity there. Trans means two groups. But you could also call this what? E also works, okay? Because the high priority groups are opposite. High priority group is carbon, high priority group is carbon. But if you've got 3 or 4 groups, you can't use trans, because it's a little ambiguous. Okay, some examples of having to decide. E or Z? Oxygen or sulfur? Sulfur. Carbon or carbon? All right. Well, which group ends up being high priority? How did we do it before? Well, that's got to be iodine. That's got to be the big group, right? No, we do it one step at a time. What is this carbon bonded to? We list the high priority group for carbon H. What is this carbon bonded to? Carbon H. Well, that didn't win. Right here we get a winner. This group wins. So what is it? Z. Could you also draw E? Yeah, switch these two groups. Right here, the isopropyl and the sulfur are cis. If you make them trans, you'll have the other stereoisomer. One pitfall is you see this big iodine and you think that's the high priority group. Yeah, but you don't look at it one atom at a time. You want to do one with the 2 bromines or this guy here? Which one do you want to do?
The 2 bromines.
Do what?
The 2 bromines.
2 bromines up here? Okay. E or Z?
Were those 2 bromines together bigger than an atom?
We do it just like this here. Carbon or carbon? Well, that carbon's bonded to a C and 2 H's. This carbon is bonded to 3 H's. Yeah. You see, I mean, right there you get your winner. Basically, with alkyl chains, longer the chain is going to be higher priority. Because eventually you'll get to where it's got more carbons, okay? So that should be kind of intuitive. How about over here, though? Which group is, so up here it's that. Carbon or carbon? All right. What is the top carbon bonded to? Iodine, H, and H. What's the bottom carbon bonded to? Bromine, bromine, and H. All right. Well, the first look gets you your winner, which is higher. Iodine. Okay? They're on the same side, that's Z. Okay? 1 iodine beats 2 bromines. 1 iodine beats 3 bromines. Okay? You do it like I did it right there.
So you list like the heaviest ones first when you list those?
Yeah, when you list what's bonded, list the heavy ones first, because you really, we're not adding them up. We're not saying this adds up to higher than that. It's like aces high. IHH beats BR, BR, BR.
Okay, so you just compare like the top highest one?
First, one at a time,
Okay.
okay? I did it systematically, do it like this. You can do the other one down there if you want there. Physical properties. What's the relationship between these two compounds? They're isomers, they should have the same formula. What type of isomers? Stereoisomers. One of them has groups like this, one of them has groups like that. Okay, just projection. Same exact name. Both of these are what? 1,2-dichloroethene. They're both that. So one is cis, one's trans. That's cis. We can also call this E. We can also call that Z. I can show another isomer. There's an isomer. Do I agree that's an isomer of those? What type of isomer is this? That's a constitutional isomer of those over there. This has a different name. That's not 1,2. This is 1,1. Different connectivity. Okay? But of the stereoisomers, which would have the highest boiling point? Well, how do we judge boiling point? The one with the highest IMFs. Which one's got the highest IMFs?
Cis.
Let's see, this has dipoles like this. This has dipoles like this. Which one of these is polar? These dipoles cancel out. They're equal and opposite. This is non-polar. Do these cancel? We're just applying what we learned last week, right? Dipoles, canceling, not canceling. So we got a polar compound and a non-polar compound. Everybody agree? Which one should have the highest boiling point? The polar one. Because this one has, see, when you talk about molecules as a whole, talk about it as a whole. I mean, it's got two individual dipoles, but as a whole, you got plus up here. As a whole, this has a dipole moment. Show the dipole moment. Direction of the dipole moment. These add together to give what? Yeah. And so you have some partial positive up here and partial negative down here. But see, that partial negative of a molecule bumps into the partial positive of the next door neighbor molecule. And you get this electrostatic attraction, which we call an IMF. It's a dipole-dipole interaction. See this molecule over here, the two neighbors are like, don't like each other that much. Because there's no polarity in the molecule. Which one's most stable? Most stable. They all have the same bonds, and so the same hybridization in the bonds. Which one's the most stable? Which one of these conformations is most stable? Syn or anti? Okay, so which one of these fixed? Chlorine's opposite, or like anti, or chlorine's kind of syn, or cis? Anti is synonymous with trans. Okay? And that's just like conformation. Didn't we learn that that is not as good as that? All we're doing here is just fixing it and showing it two different compounds. Why is this more stable? Because this one, what's around these chlorines? Lots of electrons. And we're dealing with the second shell, third shell. So these electrons are pretty big. Right?
And so what, you got these electrons just bumping into each other. What does that do? It makes it sort of like nervous. Nervous energy. Right? Which is most soluble in water? Oh, that's easy. Polar one, right? See, once you learn the basics, then you just, it's all downhill from there. Just remember, got time? Look at the remainder. Okay? Remainder here. Please also for Thursday, please have worked on this warm-up sheet. Okay, this case I want you to come and have read the chapter and try to answer like A and B, and then the mechanism arrows below. Okay? So when we move into this stuff on Thursday, we're going to be kicking it up a notch. And if you're not prepared and ready to go, you're going to be like, oh, what? Okay. So tomorrow we have tests. Any last questions about tests?